Hi everyone, welcome to today's lesson and also happy Pi Day 3.14, March 14th, Pi Day. Very fitting for our circles unit. In our circles unit today, we are going to continue talking about angles in circles. In the last play pause that you watched, we talked about central angles, and in your central angle, the measure of the angle was equal to the measure of the arc. Both were measured in degrees. Today we're going to talk about another type of angle called an inscribed angle. And an inscribed angle is an angle whose vertex is actually on the circle. So different than the central angle, because the central angle's vertex was the center of the circle. An inscribed angle, the vertex is on the circle. So here we have angle ABC. ABC, and the vertex of that angle is B, and notice that the vertex is actually on the circle. The two sides of an inscribed angle are chords. We learned what a chord was in live class last week, but a chord is a segment whose endpoints are on the circle. The intercepted arc is the arc that lies between the endpoints of an inscribed angle. It's a lot of vocabulary, but what you really need to know is that your intercepted arc is the arc that's inside the angle. So arc AC is the intercepted arc of angle ABC. The degree of the inscribed angle is equal to half the measure of the intercepted arc. Half. Okay. So the central angle was equal to the intercepted arc. Your inscribed angle is half of that. So the measure of angle ABC equals half of the measure of arc AC. So if I told you the measure of arc AC here was 50, then you would know that the measure of this angle right here is half of 50, 25. Or if I went the other way, and told you that the measure of this angle was, let's say it was 30, that's half of the arc, so the arc would have to be 60. So the measure of the angle is half of the intercepted arc when we're talking about an inscribed angle. Which brings us to intercepting a diameter. So remember, a diameter cuts a circle in half. So the measure of this arc is half of the measure of a circle, 180. Okay. So if this arc is 180 degrees, then the inscribed angle that intercepts it is going to be half 180, or 90. Okay. All right. So an inscribed, or if an inscribed angle intercepts a diameter, then it is that was silly, why did I write that? A right angle. I jumped ahead in the notes. There we go. So an inscribed angle intercepts a diameter, and it's a right angle because a diameter intercepts half of a circle, and half of 180 is 90. So no matter where that angle is, if it's intercepting your diameter, it's going to be a 90-degree angle. There you go. Now, if you have some overlapping arcs, where if you have two inscribed angles intercepting the same arc. So for example, here I have an inscribed angle. It's intercepting arc AC. See it there? And then if I have arc or inscribed angle ACD, it's still intercepting arc AD. See how my red angle and my green angle are intercepting the same arc? Then that means that those angles are congruent because they're intercepting the same arc. And the measure of angle ABD will have to be congruent or equal to the measure of angle ACD because they're intercepting the same arc. So let's use those ideas to solve some of these examples. All right, in number 1, we have an inscribed angle, and I know it's inscribed because its vertex is on the circle. So an inscribed angle is always half of the measure of the arc. If you need to write that somewhere, you definitely can. You might even see it on some of my notes in the future. But then the inscribed angle equals half of the arc that's inside of it. So if this arc is 62, then what we don't know is the angle. I'm just going to call it lowercase a for angle. The angle is half of the arc, and the arc is 62. Half of 62 is 31. So the measure of this angle, WXY, is 31 degrees. Looking here at number 2, they tell me the angle, not the arc. So I'm going to call that capital A for arc. So the angle is half of the arc. So we got to get rid of that half, multiply both sides by 2. And that will tell you the measure of that whole arc DGF. So 226 degrees. And then number 3 is an example where we see a diameter. See the diameter there? A chord that intercepts the circle. So if I want to know the measure of angle PQR, that's this angle right here. Well, the arc inside of that angle is 180 degrees, half of a circle. And the angle, that's what we're missing, is half of the arc inside of it, 90. You can do this step if you want when you see a diameter, or you might just be able to recognize that 90 right away. I'd like you to try number 4. Oh. No. Find AC first. Okay. So I'd like you to go ahead and find AC, and then we'll talk about finding BC. What's the measure of AC? Yes, the measure of AC is 2 times 47. And when you do 2 times 47, you get 94. But our answer here is not 94. And why? Well, because it's asking us for the measure of arc BC. So here's the first example where we really have to pay attention to what the question is asking, because arc BC is right here. So how can we find arc BC knowing that this green arc is 94? Well, yeah, the red arc and the green arc together are making up half the circle. So I'm going to call that red arc lowercase a. Call it whatever you want. You could call it X. But that red arc plus the green arc have to add up to 180 because they're making up half the circle. There's a diameter. So when you subtract 94 from both sides, we get the measure of arc BC to be equal to 86 degrees. Okay, let's look here at number 5. We're going to find the measure of angle JKL. Okay, angle, that's important to know. Angle JKL, that's this angle right here. So I want to know this angle. Well, that angle is an inscribed angle, and whatever it is will be half of the measure of the arc inside of it. So if I can find the measure of that red arc, then I'll be able to find that missing angle. We know that the three arcs that we see here will have to add up to 360 because all of the arcs in a circle will always add to 360. I'm going to call my big red arc here lowercase a. So the 65-degree arc, the 53-degree arc, and the missing arc, they have to add to 360. So let's see, that gives us 242. So this red arc is 242 degrees. The inscribed angle is half of the measure of the arc inside of it. So we want to know what is half of 242. That's 121. So the measure of that angle is 121 degrees. Okay, let's look at number 6. We want to find the measure of angle RST. RST is this angle right here. Remember, you follow the order of the letters. That middle letter is your vertex. So RST says we're looking for this angle here. And RUT, we'll make that a different color. How about we do blue this time? RUT is here, RUT. So that's this angle here. So now the red angle that I have there is intercepting arc RT. That's the arc that's inside of the red angle. And if you notice, that's also the arc inside of the blue angle. So that's telling me that my red angle and my blue angle have to be the same because they're intercepting the same arc. Good to know. And the measure of each of those will be half of whatever this black arc is. So let's find the measure of the black arc. We know that all the arcs in a circle have to add up to 360, and the black arc is really the only one that's missing. I'm going to call it lowercase a. You can call it whatever variable you want, but we know that the black arc, the 64-degree arc, the 139, and the 75 all have to add up to 360. So we're just going to figure out what is the measure of that missing arc. 360 minus 64 minus 139 minus 75. It's 82. So the measure of this arc is 82 degrees. So the 82-degree arc is being intercepted by this inscribed angle, this red angle, which means that the measure of the red angle is half of 82, 41 degrees. Oh, but the red angle and the blue angle had to be the same. So angle RUT is also 41 degrees. The next few examples is using the same idea, but with some algebra. So I'm going to show you how to set each of these up and then let you do a few on your own. In each of these examples, we have an inscribed angle. The inscribed angle is half of the arc inside of it. If you can remember that, you can set up any equation with any picture. Here I have an inscribed angle, angle CDE. The angle is labeled there as 8x minus 9. So the angle is half of the arc inside of it. And the arc inside of it is 158. Once you set that up, all you have to do now is solve for x using your algebra skills. Personally, I don't like this 1/2. I'm just not a fan of the fractions, and maybe you aren't either. If you're not a fan of the fractions, here's a trick. Each side multiply by 2. So what's going to happen is you can distribute your 2 to get 16x minus 18. And the reason I multiplied by 2 is to cancel out the 1/2. 1/2 times 2 is 1, so those will cancel. And so you're just left with 158 on both sides. You have a different way to solve that's perfectly acceptable. This is just how I get rid of the fraction on the first step. And now I can add 18 to both sides. Get 116x equals 176 and divide both sides by 16. So x equals 11. If you solved this differently algebraically and you still got x equals 11, that's perfectly acceptable. So number 7 was an example when your expression or your x value was in the angle. What happens, like in number 8, when the x value or the expression is the arc? Well, if you can remember this relationship, then you can still set this up pretty easily. Okay. So the inscribed angle, in this case, the inscribed angle is 67, equals half of the arc inside of it. And the arc inside of it is 4x plus 58. I'm going to get rid of that 1/2, and I'm going to multiply both sides by 2. This is not how you have to start the problem. You could distribute the 1/2 if you wanted. I'm just going to get rid of the 1/2 right away. So 2 times 67 is 134. And 1/2 times 2 is 1. They cancel. So now I get 134 equals 4x plus 58. Subtract 58 from both sides and divide both sides by 4. So x equals 19. Make sure you answer the question, solve for x, we're good. Okay, let's look at the next examples. All right, number 9, they're trying to be tricky. Right, but in number 9, I see a diameter. and I know a diameter cuts a circle in half. So that means that this arc right here has to be 180 degrees. So now we can just use our relationship. The inscribed angle is half of the arc inside of it. So you just have to ask yourself which one's the angle and which one's the arc. In number 9, the angle is 13x minus 1. The arc is 180 degrees. And so you could say half of 180 degrees, or you know what half of 180 degrees is. It's 90. Add 1 to both sides. Divide by 13. X equals 7. It was just asking us for x, so we can stop right there. Let's look at number 10. Number 10, we have an angle right here, 7x plus 6, and that angle is going to be half of this arc, but I don't know the measure of this arc. So now we have to use other pieces of the circle to help us find the measure of the red arc. And once I know the measure of the red arc, I can use that to find my missing angle here, which will help me find x. So one key piece of information I see here is this 114 degrees. So this angle is 114 degrees. It's going to be half of the arc inside of it. So I'm going to multiply 114 times 2 to tell me the measure of that blue arc. Now I know the measure of the blue arc. I knew the 76 or 78 degree angle out here, and we're missing the red arc. So maybe I'll call that red arc A. And we know that all of the arcs in a circle have to add up to 360. So now I can figure out the measure of the missing arc. I'm just going to do 360 minus 228 minus 78. We get 54. So now I know that this arc measure is 54 degrees. Now we can jump to using our equation. The inscribed angle, okay, that's 7x plus 6, is equal to half of the arc inside of it, 54. You can multiply both sides by 2 if you want, or you could just multiply the 1/2 by the 54, whatever floats your boat. I'm going to multiply both sides by 2. Distribute your 2, so that's where I got the 14x plus 12. Half times 2 cancels out and gives me 54. Subtract 12 from both sides, 42. Divide by 14, and x equals 3. If you solved it slightly differently algebraically, you still get x equals 3, and that's fine. But this one, we had to find the missing arc first, and then use that for our equation. We're going to do a similar thing here, number 11. They tell us a 92 degree arc and a 162 degree arc, but they don't tell us AC. So we're going to have to figure out what the measure of arc AC is, and then use the relationship for our inscribed angle. And we're going to have to do a very similar thing in number 12. I'd like you to try number 11 and 12. Go ahead and try them. It's okay if you get them wrong. And then once you're finished, we can go over them. So go ahead and do that now. So for number 11, you should have gotten x equals 9. And for number 12, you should have x equals 17. Let's talk about the steps for those. So in number 11, we had to find x, right? So solve for x. Well, we knew this angle, and this is an inscribed angle, so that was going to be half of the arc inside of it. But they didn't tell us the measure of the arc inside of it. We know that the entire measure of a circle is 360. So we can take 360 and subtract 162 and subtract the 92 to tell us that missing arc was 106. And now I know the inscribed angle is 7x minus 10, and the arc inside of it's 106. So we can say that the inscribed angle equals half of the arc inside of it. I multiplied both sides by 2 to get rid of my 1/2. You could have just multiplied half of 106. It doesn't matter. You can choose whichever way you want to solve. I multiplied both sides by 2. So when I multiplied the left side here by 2, I got 14x minus 20, and multiplying the right side by 2 canceled out my 1/2, leaving me with 106. Added 20 to both sides to get 126, 14x equals 126, and divide both sides by 14. In number 12, we needed to solve for x again. They told us that this arc RS was 5x plus 21. They did not tell us the measure of arc QS. But we know this inscribed angle here is 67. And I know the inscribed angle is half of the arc inside of it. So I just multiplied 67 times 2, and that told me the measure of arc QS is 134. And now I know the measure of arc QS, and all of the arcs in a circle have to add up to 360. So I said, okay, well, I'm going to take 120, that arc, add it to the 134 degree arc, and add that to the 5x plus 21 degree arc. Altogether, they have to add up to 360. So then I combine my like terms. I get 5x plus 275 equals 360. Subtract 275 from both sides and divide by 5. If you didn't see that initially, hopefully you see that now. And any further questions that look like this, maybe you'll have a better idea of how to set it up. Let's look at the next ones. All right, the next two examples are just examples where they give you all the information in like writing and you have to label it in the picture. Not a big deal, we can do that. So it says the measure of angle FGH is 6x plus 21. I'm going to go ahead and write 6x plus 21 right here on the angle. And the measure of arc FJH, okay, that's an arc, this guy, is 17x minus 28. We need to find the measure of arc FJH. So we're going to find the measure of that red arc. It is very important that you're paying attention to whether it's an angle or an arc. Okay, if it's an angle, then you label the angle. If it's an arc, then you label the arc. But you have to pay attention to those labels, otherwise you're going to set up your equation wrong. And the equation says that the inscribed angle is half of the arc inside of it. And the arc inside of this angle is 17x minus 28. Okay, and I'm going to multiply both sides by 2 to get rid of that fraction. I just don't want to have to deal with a fraction at any point. And I know that half of 17 is not going to be pretty. So I'm just going to multiply both sides by 2 so I don't have to deal with the fraction. Distribute the 2, 12x plus 42, and half times 2 cancels. That's why I multiplied by 2. So I get 17x minus 28. I'm going to subtract 12x from both sides. Add a 28 to both sides. 70. And divide both sides by 5. I make sure I answer the question, and the question said find the measure of arc FJH. Oh, that's not the answer, that's just x. So I need to find arc FJH, which they gave to me, 17x minus 28. So I can say the measure of arc FJH is 17 times 14 minus 28. So my final answer is 210 degrees. Okay. I'd like you to go ahead and try number 14. They tell you an expression for angle STU. They give you an expression for arc SU. And then after you solve for x, you need to find the measure of angle STU. Go ahead and try that one now. Okay, so for number 14, you should have gotten x equals 9. And when you plugged that into angle STU, you should have gotten 29 degrees. So when you label the picture, angle STU, the angle is 5x minus 16, and the arc SU is 12x minus 50. Angle STU is an inscribed angle. Its vertex is on the circle. So the measure of the inscribed angle is half of the arc inside of it. So here's the angle that is half of the arc that's inside of it. I multiplied both sides by 2 to get rid of my fraction. So when I multiply the left side by 2, I get 10x minus 32. And multiplying the right side by 2 cancels out the 1/2, leaving me with just 12x minus 50. I subtracted 10x from both sides, so I got negative 32 equals 2x minus 50. Added a 50 to both sides, and then divided by 2. And x equals 9 is beautiful, but it's not the answer to the question. The question said to find the measure of angle STU. So I had to find the expression for STU, plug that 9 in, 5 times 9 minus 16. So my final answer is 29 degrees. All right, so number 15 deals with some overlapping angles. Let's check that out. It says the measure of angle ABD is 6x plus 26. ABD, that's right here. I'm going to write it kind of small. 6x minus 26, that's this angle. And angle ACD, let's use a different color. Let's do blue. ACD, that's this guy right here, is 13x minus 9. You can see why they give it to you sometimes in words instead of in the picture, because it's so small. We need to find the measure of arc AD. Let's make that green. So at the very end, we're going to find the measure of this arc. Okay, well, if I look at angle ABD, I see that it has this chord and this chord, and it's intercepting that green arc. Nice. And when I look at the blue angle, angle ACD, that's using this chord and this chord, and it's still intercepting that same arc. Ah, the red angle and the blue angle intercept the same green arc, which means the red angle and the blue angle have to be congruent because they're intercepting the same arc. So I can say, oh, well, 6x plus 26 is going to have to equal 13x minus 9. So we can use that to solve for x. Subtract 6x from both sides, add a 9 to both sides, and divide by 7. So we get x equals 5. So now I can take that and I can plug it into either one. I'm going to get the same number, whichever one I choose to plug it into. 6 times 5 plus 26, or 13 times 5 minus 9. We get either one, you get 56. Okay, so this angle is 56 and this angle is 56. So now to find the measure of the green arc, the arc is going to be twice as much as the angle. Remember, the inscribed angle is half of the arc. So if the angle is 56, we need to find the measure of that arc. Multiplying both sides by 2 tells me that that arc measures 112 degrees. So the measure of arc AD is 112 degrees. Number 16. I see a triangle in number 16. That's nice. And it's going to be a right triangle. Why is it a right triangle? Well, because this angle right here, angle JKL, is intercepting the diameter, or this 180 degree arc. And half of 180 is 90. Now the measure of angle JKJL is 3x plus 2. So follow those letters in order. KJL, that's this guy right here. That's 3x plus 2. And angle KLJ, follow those letters in order. That becomes this angle over here. That's 7x minus 32. So now how could I solve for x? Well, let's go back to the very first shape we recognize there as that triangle. Remember what the three angles in a triangle add up to? Yeah, they add up to 180. So I can say 90 plus 3x plus 2 plus 7x minus 32. They have to add up to 180 because those are the three angles in the triangle. So we can solve for x. We get 10x plus 60 equals 180. When you combine our like terms, subtract 60 from both sides and divide by 10. All right, so x equals 12. We are really looking for the measure of arc KL. Arc KL is this little dude right here. Well, that angle, or that arc, is being intercepted by this angle. So I'm going to take our x equals 12 and plug it in. 3 times 12 plus 2. 3 times 12 is 36, plus 2 is 38. So this angle right here is 38 degrees. The inscribed angle is half of the arc inside of it. So if I multiply both sides by 2, that tells me that the measure of arc KL has to be 76 degrees. All right, now sometimes we might not have just an inscribed angle, or we might not have just like an inscribed right triangle. We might have an inscribed quadrilateral. If that happens, then you can go ahead and know that the relationship between opposite angles is going to be supplementary. So if a quadrilateral is inscribed in a circle, inscribed meaning it's inside and all of its vertices are on the circle, then its opposite angles are supplementary. So in my picture here, in this example, that means the measure of angle A plus the measure of angle C will be 180 degrees. And you could also say the measure of angle B plus the measure of angle D will be 180 degrees, because those are the angles that are opposite each other. That relationship can help you find some measurements, especially if you find yourself being stuck. Ask yourself, do I see an inscribed quadrilateral? Sometimes that really will help unstuck you. Yeah, that doesn't make sense. Help you get unstuck. How's that? So in number 1, I see the angle J is across from angle L. Those are the angles that are across from each other in the quadrilateral. I don't know angle J, but I do know angle L. So I can say, well, whatever J is plus angle L has to add up to 180. And then I can do kind of the similar thing here for K and M. K and M are across from each other. I don't know angle K, but I know it's across from angle M, and they are inscribed in that circle. So I can say, oh, well, angle K plus 45 has to be 180 degrees. And once you know that, then you can just go ahead and solve for J and K. Subtract 92 from both sides. So angle J is 88 degrees. Subtract 45 from both sides, and angle K is 135 degrees. All right, let's look at number 2. Number 2, we have 126 degree arc over here for arc PQ. And we know that arc PS is 90. We don't know arc SR, we don't know arc RQ. We do know that angle Q here inside is 93 degrees. So there's a couple things that we can do. And there are different ways to solve this. So if you think of it a slightly different way, it doesn't mean that you're wrong, it just means that you thought of it slightly differently than I did. So I'm looking right here at the one angle that I do know, angle Q. That's 93 degrees. It's an inscribed angle because its vertex is on the circle. And the arc inside of it is this entire green arc, this whole thing. Okay, so the angle is half of the arc. So if I do 93 times 2, that tells me that this entire green arc is 186 degrees. Okay, well, if the entire arc is 186 degrees and this piece over here, let's do a different color, do orange. This piece is 90, so that tells me I can find arc RS. This entire green arc is 186, a piece of it is 90, so I'm just going to do 186 minus 90, and that will tell me that arc RS is 96 degrees. Now that I know three of those four arcs in the circle, right? We're missing one arc. Right here, we're missing this little guy. We can still find that arc because we know that all of these have to add up to 360. So I'm going to do 360 minus 126 minus 90 minus 96. So this little arc right here is 48 degrees. Okay. We also know that this inscribed quadrilateral, the opposite angles are supplementary. So I know that angle S plus angle 93 has to add up to 180. So I can find angle S quite easily. Just subtract 93 from both sides. So angle S is 87 degrees. Now we just need to find angle P and angle R. So let's see. I'm going to erase some of my markings here. 96 and 48. All right, we know this is 96 and we know this is 48. We know this is 87. Now we know angle P is also an inscribed angle. It is an inscribed angle. Here's a chord and here's a chord. And the arc inside of it is this entire arc. Okay, well, that arc is made up of two pieces, 96 and 48. So 96 plus 48 tells me that this whole arc is 144 degrees. The inscribed angle is half of the arc inside of it. So half of 144 is 72. So the measure of angle P is 72 degrees. And we know that angle P and angle R are opposite each other in the inscribed quadrilateral. So I can say, oh, well, 72 plus angle R has to add up to 180. So 180 minus 72 will tell me that angle R is 108 degrees. Beautiful. Okay, so a few of these we had to use what I like to call arc addition, very similar to segment addition. So when you add two arcs together. So like when we had to find angle P, I had to add 48 and 96 together. Or when we found that 48 degrees, we had to know that the measure of the whole circle was 360. Using those ideas, see if you can figure out number 3 and number 4. Just try it. See what you can figure out. If you don't get it, you don't get it. But just try it and see what you get, and then we'll go over it. So go ahead and try number 3 and number 4 now. Let's see how you did on number 3. Okay, so on number 3, I recognized that this angle 51 was an inscribed angle. The arc inside of it was this arc right here that I kind of have in blue, right? Well, the angle is half the arc. So 2 times 51 is 102. So arc VWX was 102 degrees. I already knew a piece of it. A piece of it was 67. So I did 102 minus 67 to tell me the other piece, 35. So then I could say, okay, well, the whole entire circle has to be 360. If I know this piece is 35 and this piece is 67 and this piece is 101, then I can subtract all of that from 360 to tell me the last missing arc, and that's 157. So now I know the measure of all of the arcs. I can find the measure of the angles. First thing, Y and W, those are opposite angles in my inscribed quadrilateral. So if I do 180 minus 51, that tells me angle W is 129 degrees. Then I try to find angle V. So angle V I have here in green. It's intercepting this green arc, and this green arc is made up of the 35 degrees and the 157. And when I add those together and then divide by 2, because the angle is half of that, that tells me that angle V is 96 degrees. Now that I know that angle V is 96 degrees, angle V and angle X will have to be supplementary. So I take 180 minus 96, and that's how I got the 84. Okay, so go ahead and try number 4 now. Maybe that explanation gave you a little clue to how to do parts of number 4. So tell me your answers for number 4. All right, so in number 4, you had one missing arc. It was right here, arc AD. So hopefully you recognize that the entire circle measured 360, and you could subtract 147, 61, and 39 to find that missing arc AD at 113 degrees. So then I chose to find angle B. Angle B was an inscribed angle, and the arc inside of it was this entire green arc, the 113 and the 147. So the angle is half of the arc. So I add 147 and 113 together and divide by 2. And I got B was 130. Once I knew B and D had to be supplementary because they're opposite angles in that quadrilateral. So I can say, oh, well, 180 minus 130 is 50. So now angle D is 50 degrees. Then I wanted to find angle C. Angle C is an inscribed angle here in red, and it's intercepting arc BAD here in red. The angle is half the arc. The arc is made up of 39 and 113. So I add 39 and 113 together. That tells me the measure of that arc. Divide it by 2 to tell me the measure of angle C. Angle C is 76 degrees. So now I know angle C. And angle C and angle A are opposite angles in the inscribed quadrilateral. So I can just take 180 minus 76, and that's where I got the 104 degrees. Right, each of these examples uses the idea of opposite angles in an inscribed quadrilateral being supplementary. I'm not going to go through every single one of these. Maybe we can just set them up though, right? Like here, number 5, angle G and angle E are opposite angles in that inscribed quadrilateral. So if I wanted to solve for X, I can add my opposite angles together. They have to sum to 180 to be supplementary. Same idea here, number 6, opposite angles will add up to 180, and you'll solve for X. In number 7, they don't tell us angle N, but you could easily figure out angle N because angle N is an inscribed angle. And in that inscribed angle, you have this arc, 91 plus 135 is 226, and half of 226, 113. So now you know angle N. And so now you can say, oh, well, angle N and angle L are opposite angles in an inscribed quadrilateral. They must be supplementary. So sometimes they don't give you every single piece that you need for your equation, but they give you all of the clues you need to figure out your missing piece. And let's see, number 8, very similar idea. Angle J and angle H are going to be supplementary. We know angle J, but we don't know angle H just yet. But we do know angle H as an inscribed angle will be half of the arc inside of it. And the arc inside of it is going to be 50 plus 96, 146. And half of 146 is 73. So angle H is 73 degrees. So now you know angle J, and you know angle H, and you can use that to solve for X. Okay, I'm going to let you solve these. I don't think you need to watch me do all of that algebra. You're welcome to check your answers on OMHS. If you catch a mistake, let me know. I don't think there is one though. Or if you have any questions, that's another one. If you have any questions, please let me know and I'm happy to help. Okay, I'm going to let you do number 9 on your own also. Let's talk about tangents, the last big idea for today. A tangent line is a line that intersects a circle at exactly one point. We have heard the word tangent before, and that was when we were talking about sine, cosine, and tangent using our trig. And for now, I'm going to say they're two different things. Eventually, in your future math classes, you're going to see how they actually relate to each other. But we're just going to say that a tangent line is different than using the tangent button in trig. Okay, it's just different. A tangent line intersects a circle at exactly one point, and the point where it touches the circle is called the point of tangency. Okay, so here in my circle, I have circle P, and it's being intercepted by line AB, and line AB touches the circle one time right there at A. A is the point of tangency. Okay, the one place where it touches the circle. A line is tangent to a circle if and only if, there's our biconditional statement, it is perpendicular to a radius. Okay, so here's the radius PA. If it makes a right angle with that segment and that segment intersects the circle one time, then it's perpendicular. So what does that have to do with any examples we might see? Well, our friend Pythagoras is going to come back to visit. So hopefully we like the Pythagorean theorem. Remember that Pythagorean theorem, c² equals a squared plus b squared, that Pythagorean theorem will help us determine whether or not it's a right triangle. So if it's a right triangle, that means you have a right angle. And if you have a right angle, that means you have perpendicular segments. And if you have perpendicular segments, then you've got a tangent line. That's going to be our thought process for each of these problems. If you don't have a right triangle, then you don't have a tangent line. Okay, so let's look at number 1. Potentially, this would be a right angle. We're not sure if it's a right angle yet. That's what we have to determine. So we're going to use our friend Pythagoras still, but we're not going to put the equal sign just yet. The hypotenuse here would be 17. So 17 squared. We want it to be equal to a squared plus b squared. 17 squared is 289. And hey, calculator, what's 8 squared plus 15 squared? Oh, it's 289. They are equal. That works. So I have a right triangle, which means I have a right angle, which means that PA and AB are perpendicular, which means AB is tangent. So is it tangent? Yes, it is. Okay. Sometimes they get tricky and they don't give you the whole piece. So don't be tricked by this. What is the hypotenuse if this was a right triangle? Okay, so if this was a right triangle, if I could put this symbol here, what would the hypotenuse length be? If you said 5, I tricked you. First, think about that. Can't be 5. The hypotenuse is always the longest side of a triangle. And if the longest side was 5, that means the legs would have to be smaller than 5, but they're not. So what on earth is the hypotenuse? Well, we know that the radius is 11. And in a circle, every radius is the same length, which means this radius is 11. So the hypotenuse here is 16. So does 16 squared, does that equal 11 squared plus 14 squared? 16 squared is 256. And 11 squared plus 14 squared is 317. Those are not equal. You can put the not equal symbol. If you really wanted to put a less than, you could. But what this tells me is this is not a right triangle. If it's not a right triangle, then I don't have a right angle. And if I don't have a right angle, then I don't have perpendicular sides. And if I don't have perpendicular sides, I don't have a tangent. So no, it's not a tangent. Okay. Number 3 and 4 are saying, okay, we're telling you it is tangent. We're not asking you if it is, we're telling you it's tangent. So as soon as you know that the line is tangent, you can go ahead and put that right angle symbol there. You know that's going to be true. Find the value of x. Ah, all right, well, Pythagorean theorem, right? Go ahead and use that Pythagorean theorem that we've grown to love so much and solve for x. Go ahead and round it to the nearest 10th. Yeah, round to the nearest 10th. Try that now. All right, you should have gotten 20.2. The hypotenuse was x, so x squared equals 7 squared plus 19 squared. To undo your square, you have to use the square root. You get the square root of 410, and to the nearest 10th, it's about 20.2. Be very careful in number 4. What is the hypotenuse in number 4? You said 18, you are correct. Why? Well, because the radius is 11, which means this radius is 11. So the hypotenuse is 18. So now that you know that the hypotenuse is 18 and this radius is 11, can you find the length of the tangent segment? Do that now. All right, you should have gotten 14.2. You can check your answer with what you see here. Hopefully this is getting easier. Right, and then we have just a whole bunch of examples here of finding the value of x as long as JK is tangent to the circle. So anytime you hear someone say that it is tangent to the circle, know that it touches the circle only one time and it's perpendicular to a radius. So that means you have right triangles in all of your pictures here. Okay. Do be very careful in number 8. Notice that x is a radius. So when you find the length of JM, to find X, X will be half of JM. Okay, I'm going to let you just practice these on your own. Check your answers with the key on Edmodo. My honor students, number 9 is definitely a challenge one. If you're not in honors, go ahead and just skip number 9 right now. But if you are in my honors class, I highly recommend that you try it. And even if you're not in my honors class and you want to try it, go for it. The answer key is on OMHS. The algebra used here is not algebra really used on a geometry SOL, but it's definitely algebra that will be helpful when you get into Algebra 2 next year. All right. And then a little bit more on tangents. Okay, we talked about how a tangent line only touches a circle once and it's perpendicular to the radius. Maybe you would see an example that looks like here where I have 2 segments that are tangent. If that happens, so here if AB is tangent to the circle and BC is tangent to the circle, then AB is congruent to BC. Simple as that. And that happens even if you have a whole bunch of tangents. So like here it says a polygon is circumscribed around a circle. Circumscribed is just a fancy way of saying on the outside of the circle. Then all of the sides are tangent. So if you see a picture where you have a circle that is inside of a triangle and it's touching the triangle like this, and you can say, oh, well, these 2 segments are congruent. You're allowed to say that these 2 segments are congruent. And you're allowed to say that these 2 segments are congruent. Okay, and we're going to see some examples of that. I'm not going to do every single example that you see here, but we'll start with number 10. Number 10, it says, assume that segments that appear to be tangent are tangent. So in number 10, AB is a tangent and CB is a tangent. If you have 2 tangents to a circle, then they intersect, then those tangents are congruent. So you can just say 5x plus 23 equals 8x minus 19. And then you can just solve for x. Subtract 5x from both sides. Add 19 to both sides. Divide by 3. Simple as that. It's going to be the same idea here in number 11. You're just going to have to take that x and plug it in for PQ. I want to show you an example like number 12 and number 13. In number 12, it said find SV. I'm going to call SV Y. It's just easier to have a variable to solve for than the name of a segment. So I'm going to solve for Y. Okay. Well, I know that these are tangent, which means I know I have a right triangle here and a right triangle here. I know that TV and VU are radii of the circle, so UV has to be 17 also. All right, well, since ST and SU are both tangent, then I can say, well, 10x minus 41 has to equal 4x plus 7, since they are both tangents to the same circle and those tangents intersect. So we subtract 4x from both sides, add 41 to both sides, and divide both sides by 6. So x equals 8. I'm going to take that 8 and plug it in for either one, really. 10 times 8 is 80, minus 41 is 39. You could have done that for SU and been the same thing. Okay, now we want to actually find SV. That's going to be our final answer here. But now that I know the length of ST and I know the length of TV and I know it's a right triangle, now I can just say, oh, Pythagorean theorem. Hypotenuse squared equals leg squared plus leg squared. Okay, so 17 squared plus 39 squared gives me 1,810. Take the square root of both sides. We get about 42.5. There it is. All right, let's look at number 13. It says to find the perimeter. Okay, so let's go back and review what perimeter means. Perimeter is the sum of the lengths of the sides. So if I wanted to find the perimeter of DEF, triangle DEF, I need to find the length of DE, EF, and DF and add those together. That would be the perimeter. So let's go piece by piece. We have tangents in our circle. So DG and DH will be congruent. And since I know DG is 11, I know DH, they have to be the same. And then we also have tangents HE and EI. Those are going to be congruent because they are tangents to the circle and they intersect. So since HE is 16, EI will be 16. Okay, and then we've got GF and FI. Those are tangents that intersect. So GF will all have to be 9.5. So to find the perimeter of the whole triangle, I'm going to add all of the lengths of the sides of that triangle together. 11 plus 11 plus 16 plus 16 plus 9.5 plus 9.5. Maybe you found a shorter way to add these together. Either way, you should get the perimeter is 73. Sometimes they get a little tricky on us. So let's look at number 14. I like to use colors to show what's congruent. If you like to use the colors too, be my guest. I think it's a great idea. Okay, I know that these two tangents are going to be congruent because they are tangent and they intersect at P. The tangents that intersect at Q, I'm going to make here in green. The tangents that intersect at R, I'll make blue. And the tangents that intersect at S, run out of colors, orange. Hopefully you can see orange. Okay. So now I'm going to use what I know about the congruent parts to fill in what I don't know. So I know that this red piece, can't see what I'm pointing to. Here we go. I know that this red piece is 23, which means this red piece is 23. So I'm going to go ahead and label that red piece 23. Okay. Now I know that the entire length of PQ is 37.5. And this red piece is 23. So I can subtract 37.5 minus 23, 14.5. So the green piece here is 14.5. I'm going to label that 14.5, which means this green piece is 14.5. Okay, well, I know that blue piece there is 27.1. So that means this blue piece is 27.1. Okay, well, this entire length is 52.5. The blue piece here is 27.1. These actually touch here, right here at the tangent point. So this blue piece is 27.1 and the whole thing's 52.5. And I'll just subtract and find that that orange piece is 25.4. And if the orange piece is 25.4, then this orange piece is 25.4. So to find the perimeter of this quadrilateral, I'm going to add all of the lengths of the quadrilateral together. You can add each small piece together, or you could find the length of each side and add those, whatever makes you happy. You should get 180. So when you add 23, 14.5, 14.5, 27.1, 27.1, 25.4, 25.4, and 23. You add all the lengths of that quadrilateral together to get its perimeter. All right, so we covered 3 big topics in today's lesson. We covered inscribed angles. We covered inscribed quadrilaterals, and we covered tangents. If you have any questions about any of these, please reach out to me. I'm happy to help. There are practice problems available to you on OMHS, so please check those out. And your attendance quiz word was given to you in one of the pauses in the play posit. So I hope you got that. Let me know if you have questions. I'm happy to help, and I look forward to seeing you live in class on Wednesday. Have a great day, everyone.